So we're continuing on our journey into this carbonyl chemistry. And one of the more interesting things that carbonyl chemistry, or one of the more interesting aspects of carbonyl chemistry, in my opinion, is that when you have a carbon-carbon bond that is what we call conjugated to a carbonyl group or a carbon double bonded oxygen, like we see in propanol here, this is called an alpha beta unsaturated carbonyl carbon compound. So it's an alpha beta unsaturated carbonyl compound. And just like a lot of times we talk about alpha hydrogens, the alpha carbon is the one next to the carbonyl group, and then the beta carbon is the one next to the alpha carbon here. And so when we say it's alpha beta unsaturated, this is what we're talking about. Now, when we see this, there is resonance here. So one of the things to be aware of is that we have resonance where these electrons are delocalized in this spot, and then these electrons are delocalized up here. Again, remember, these two things don't actually exist, right? The electrons are spread out. But when we represent this using a resonant structure, what we see here is that the beta carbon has a positive charge and the oxygen here has a negative charge. Now, when we look at the resonant structure, what we see then is when you see the resonant structure, which is like this, we now have two electron pore sites. We have the carbonyl that we've been talking about this whole chapter, but now we also introduce this beta carbon that also has a partial positive site as well. And for us, that means that's a reactive site. So that means that nucleophiles can attack in two positions, either at this carbonyl carbon or the beta carbon shown here. I do love a good connection to kind of life overall. We talk about propanol, which we're showing here. It's commonly called acrolein, and it's used as a herbicide to control algae and aquatic weeds in irrigation canals. But it's also produced when glycerol from fat or oil is burned, such as in the cooking process of deep fried foods. And there's some pretty interesting articles that came out about 20 years ago, asking the question, does this acrolein, does propanol cause cancer, right? Are you more likely to have cancer if you eat a lot of fried foods? Which is just kind of an interesting side there. And you're more than welcome to research that more if you're interested. Now, I want us to look at the mechanisms. This can undergo two different mechanisms or two different reactions, and so that means we get two different mechanisms. So one of the mechanisms here is what we call a direct 1,2 addition mechanism. So we're going to draw our molecule, right? And then I'm just going to use a general nucleophile, which has got a negative charge there. In this 1,2 addition, what happens is the nucleophile, which is negative, is going to attack the partially positive carbonyl carbon. Those electrons are going to go there. Okay. Now, once that happens, we're going to follow our arrows. That's a nucleophilic addition. Okay. And here, then we are going to have an acid, which I'm going to represent with a generic HA. And what's going to happen is we're going to get a proton transfer reaction. And then when that occurs, we've attached the nucleophile, and we also end up with an alcohol functional group. Now, the reason this is called a 1,2 addition is because we number these atoms as 1, 2, 3, 4. And so with that numbering, what we see is that the species that are added, which is the proton here and the nucleophile here, are added to the 1 and the 2 carbon. Okay, so these guys here are added. I said carbon, but it's to the 1 and the 2 atoms. Okay, now and this is also called a direct. It's also known as a direct addition. So it's known as a 1,2 addition. You're going to see that a lot. There's a synonym that's a direct addition. The book merges these to say it's a direct 1,2 addition mechanism, but know that we have a lot of different synonyms for this particular mechanism. Now, I said earlier there were 2 places that were partially positive, right? We have this place which is partially positive and this place which is partially positive. So when we look at the direct 1,4 addition, what we're going to see is that the nucleophile there is then going to attack the 4 position, that partial positive. So let's look at that mechanism. So again, we're just going to draw the exact same molecule. Okay, we have a nucleophile. And so what's going to happen then is that nucleophile is going to come in and attack that 4th atom, right? So if we name these as 1, 2, 3, 4, and remember, this carbon's partially positive and this carbon's partially positive, it's going to attack the 4th atom here. These electrons are going to go up there, and then those electrons are going to go there. Again, it's a nucleophilic addition. And so then the nucleophile is attached to the 4th atom, which happens to be a carbon. If we're following our arrows, we can see, right, that now we have a double bond. We've got an oxygen. It's got a negative charge. And then we have a hydrogen there. Okay? Now, this can go through a proton transfer reaction. Right? And when it goes through a proton transfer reaction with a generic HA, then what we see here is that this oxygen is going to come and attack that, and those are going to go there. And so now we have a nucleophile that's attached to the CH2. We have a CH, a double bond here, a C, an OH, and an H. Okay? And these species have added to the 1, 2, 3, 4, to the 1 and the 4 atoms. And that's why it's called a conjugate addition or a 1,4 addition. Those are synonyms, or as he's done in the book, conjugate 1,4 addition. Now, I want you to notice something. Something should be blaring out to you here. And what should be blaring out to you is that's an enol. So that is going to go through an autontomerization mechanism, and where you get the keto form. So it's the nucleophile, CH2, CH2, and then C double bond OH. And so we get our keto form. So it undergoes this. Now, there's a few things to be aware of here as far as naming. When we talk about this, if a carbon nucleophile adds by a conjugate addition, which is what we're seeing here, and forms a carbon-carbon bond, that process is called a Michael addition or Michael reaction. And this is where a carbon nucleophile adds by conjugate addition. And now that's after the American chemist Arthur Michael, who lived from 1853 to 1942. However, over the years, the term Michael reaction has evolved into a generic description of conjugate additions involving any nucleophile. I honestly think that this terminology will fade away. Chemists are trying now to go from these reactions that are named after people. Obviously, we still have a lot of work to do. Into kind of more descriptive ideas of what they do. So like this is a 1,4 addition or a conjugate addition. I think 1,4 personally is my favorite way to describe this. I think Michael addition gives you no hints or tells you anything about this. But I still need to touch on this in case you see Michael addition somewhere else, the MCAT, the DAT, any of those things. I still want you to be able to recognize it. And so, or if it's in your homework, right? So you need to understand that these are all synonyms for the same thing. Conjugate, 1 addition, 1,4 addition, conjugate 1,4 addition, or a Michael addition. All synonyms for this. Now, I'm sure the burning question in your heart is, Dr. Pierce, do these two things happen at the same time? Are there conditions which might favor one over another? And the answer to that is, why, yes, there are conditions that can favor one over another. I have cut off, this should be 1,4, not 1,4. That should be I've cut it off as I was moving the image around. Let me back up. So, 1,2 or 1,4, which one's going to happen? Well, it depends mostly on whether the nucleophile adds to the carbonyl carbon reversibly or irreversibly. And we've seen this before. And so nucleophiles that add reversibly to the carbonyl carbon tend to yield the conjugate addition product, right? And remember, the conjugate addition product is the 1,4. And the nucleophiles that add irreversibly give us the direct addition product, which is the 1,2. So, of course, reversibly gives us those equilibrium arrows. The very first, if you just have one arrow, that gives you the irreversible. So, now we have to decide if our nucleophiles add reversibly or irreversibly. And so we have a really nice table here. And basically, it depends on the charge stability that each side of the reactants exhibits, right? So nucleophilic addition tends to be irreversible if the negative charge that develops in the adduct is substantially better stabilized than it is in the nucleophile, okay? So in practice, what we see is that nucleophilic addition to a carbonyl carbon tends to be irreversible when it involves a very strong R-, so an alkyl, a carbanion basically, or a hydride nucleophile, okay? So these reactions here, right? Grignard, alkyl lithium, Wittig, lithium hydride, sodium borohydride are examples of nucleophiles that add irreversibly. Everything else tends to add reversibly. So if I were you, I would memorize the things that add irreversibly because it's R- or H-, carbanions or hydrides, right? That's what I would memorize. And that's really, that's really the best way to do this. Let's look at some examples. So, for example, we have C6H11MgBr, which you should, right, look at that and be like, hey, I think that's a Grignard. And hey, I think when we talk about a Grignard here, right, that is going to add irreversibly because we know we can simplify Grignards to that, okay? So we have this very strong carbanion, and so it's going to add irreversibly to the carbonyl carbon, and the major product here, which is shown right here, is the 1,2 addition product. So this is an example of one that adds irreversibly. Now, on the other hand, if we look here, right, this can be if we take away the sodium, which is a spectator ion, this is CH3O minus, and that adds irreversibly. So the major nucleophilic addition product is from a conjugate addition. So it's that 1,4 addition product. That's what we see. So let's do an example. Draw the mechanism that leads to the major product for the following reaction. Now, here's what we are going to look at, okay? The very first thing that you need to be able to do is identify that this is an alpha-beta unsaturated carbonyl. You need to start looking for that with reactions, right? And so this is an alpha-beta unsaturated carbonyl, okay? Now, what's the nucleophile? When we look at this reaction, you should zoom in right here. No, potassium's a spectator ion, so the nucleophile then is going to be the cyano group, okay? Can the nucleophile attack more than one electrophilic site? Well, the ketone is alpha-beta unsaturated, so, right, it can either attack, right, that carbonyl, that partially positive carbon, or the carbonyl carbon, depending on whether it's a 1,2 addition or a 1,4 addition. So then the next thing that should pop into your head is, okay, is this going to be reversible or irreversible? So when I go back and look at the table, right, where does this fall? And so I can't go back here in this particular program, but if you go back and you look at table 18.2, and what you should see is the second from the bottom is NC, just like this, minus. And that falls under reversible. Okay, so that's not one of those R minuses, right? This falls into a different category. It's reversible. And so then you need to know, because it's reversible, the 1,4 addition is going to be the major mechanism here. And so then it says in a 1,4 addition, where will the nucleophile attack? Well, if it's a 1,4 addition, right, where will the nucleophile attack? It's going to attack the beta carbon right there. Okay, so that's what we're going to start with. So now let's start working on this mechanism. So we're going to draw our molecule, because remember, we're always going to redraw molecules. We're not going to be lazy organic chemists. I'm going to draw it on this side because it makes my life easier, right? And then the first step is going to be a nucleophilic addition reaction, where this guy goes here, right? This electron goes there, and then these electrons go up there to form we've got lone pairs now on that oxygen. This is a nucleophilic addition. And so now O minus, Cn, right? And then now we know the next step is a proton transfer. And I don't want to write it up there. It's a proton transfer. I want to write it down here. I'm going to look and see what's providing that proton. It is an acid. It's sulfuric acid, which we can write just as kind of simplify this like that. So these electrons are going to go steal that proton. Those electrons are going to go on the oxygen. Okay. And now okay, we know that here we've recognized, okay, so we've done the addition. We know this is an enol. Now we have to show the enol to keto transformation. Okay, now this is acidic. So we know the next thing that's going to happen is a proton transfer. And so what happens here, and I've got ahead of myself, so it just needs to be OSO3 there. Come on, go back and give me what I need. Okay, there we go. And so with this proton transfer, what we're going to see happening. Nope, I was right originally. I apologize. I'm just going to erase that. Okay, so the third proton transfer, or the second proton transfer, there are 3 of them. What we're going to see here for this keto-enol rearrangement is that these electrons are going to come here to form a double bond. These electrons are going to come out and grab a proton. These electrons are going to go back on that oxygen. Now we're going to follow our arrows and see what bonds are forming. And so when we look at this proton transfer here, what we're going to see for keto-enol rearrangement is those electrons are going to go there, and those electrons are going to go there. Now I want to remind you that this keto-enol rearrangement can either be acid mediated or base mediated. This happens to be an acid mediated proton transfer reaction. So when you might want to go back to chapter 7 and review that, and you'll choose that based on your conditions. But I did want to show you an example, basically just to dust off some of those brain cells, as we like to do. So maybe the burning question in your heart is why? Why does this matter? Okay. Well, why does it? Basically, when I say why does it matter, what I mean is why does the regioselectivity involving a 1,2 addition or 1,4 addition depend on whether the nucleophile adds reversibly to the carbonyl carbon? And we've talked about this in chapter 12 with electrophilic addition to conjugated dienes. And so we know that the reversibility of nucleophilic addition governs whether the competition takes place under thermodynamic or kinetic control. So if you want to go back and kind of review that information, that's chapter 12 and it's section 10. And then we also talk about thermodynamic and kinetic control in chapter 11, section 3. So if you want to kind of dust off your brain cells, it's been a minute since you've looked at that information, particularly chapter 11, that was last semester. You might want to go back and review that information. But I just want you to know, if a nucleophile adds reversibly, then the reaction takes place under thermodynamic control, and the major product is the thermodynamic product, and that's the one that's more stable, okay? And if the nucleophile adds irreversibly, then the reaction takes place under kinetic control, and the major product is the kinetic product. And I just want to remind you that's the one that's produced more rapidly. And we've talked about this like I said, in several chapters, but I just want to remind you of it here. So we want to take these ideas and apply them to nucleophilic addition. And so to be able to do this, we need to know which product is the thermodynamic product and which product is the kinetic product. So generally speaking then, the conjugate addition, which is the 1,4, right, product is the one that's more stable. And so that means it's the thermodynamic product. And then the direct addition, which is the 1,2, is the product that's made more rapidly, okay? And that's the kinetic product. So the conjugate addition product, which is shown right here, is more stable in part because of charge stability. So notice that because we have this enolate ion as the product, we've got some resonance stabilized negative charge. Okay, and so that makes it more stable. And so that's what makes it the thermodynamic product. Then the direct addition product has an isolated negative charge, and that makes it less stable. Okay, but one of the reasons it's a kinetic product is because the 1 and the 2 carbon, the 1 oxygen and the 2 carbon are closer than the 1 and the 4. So that tends to make it the direct addition product. To go on into the stability even further, if we want to look at bond energies, what we see here is that the conjugate addition product bond energy is 720 kilojoules per mole, and that makes it more stable than the direct addition product, which is 619 kilojoules per mole. So the conjugate addition leads to the overall thermodynamic product because the overall uncharged product of the conjugate addition has a greater total bond energy than the one from the direct addition. So, and that has to do with the type of double bond that's present. So hopefully you've been able to draw some similarities between what we've talked about in this particular section and what we talked about in chapters 11 and chapter 12 with these, 1,4 and 1,2 addition products. In the next screencast, we're going to talk about how these alpha beta unsaturated carbonyls react with lithium dialkyl cuprates and other organometallic reagents.